Hello, this is Eric from UNC Charlotte. We will talk today about one of the most classic algorithms that gets executed on distributed memory machines. Iterated matrix vector multiplication highlights the importance of different data partitioning techniques. It also exemplifies the power of collectives in MPI. We have a matrix A and an initial vector x0. We will generate x1 by multiplying A and x0. Then we will generate x2 by multiplying A and x1. The multiplication of the matrix by the next vector will continue for some number of iterations. This process of iterated matvec is a pattern that appears in many numerical algorithms. It is literally a power method, but a similar pattern also appears in algorithms extracting eigenvectors, used for instance in data mining. The pattern also appears in solving linear equations, which are used in various scientific applications, for instance, to do 3D reconstructions of a scene from images. In matvec, you have a square matrix A, and you have an input vector x0. We will call x1 the result of the multiplication of A by x0. A particular entry of x1 is obtained by computing the dot product of a row of the matrix with the vector. We multiply element-wise each entry of the matrix with an entry of the vector, and we sum the terms to obtain one entry of x1. With an n by n matrix, the sequential complexity is in theta of n squared. To execute such an algorithm on a distributed memory machine, we will need to partition the calculation. The owner computes rule states that this is accomplished by partitioning the data that compose the application. Here, we will partition matrix A. The simplest way to partition the matrix is to decompose it row-wise. This is what we call a 1D decomposition because each processor receives a stripe of the matrix. The processor will compute the entries of x1 that correspond to one of these rows. If we have p processors, a single processor will do theta of n squared over p computation. It will need the entirety of x0 to perform this computation. Therefore, between each iteration of matvec, the processor will need to acquire the pieces of x1 that it does not have. This will require the processor to be involved in communicating theta of n entries. One could also decompose the matrix in columns, but it essentially leads to the same result. A less intuitive way to partition the matrix is to decompose the matrix in a grid of blocks. So, with p processors, we'll decompose the matrix in square root p by square root p blocks. This is a 2D decomposition, and we will assume that p is a square number and that the matrix partitions evenly in square root p blocks of rows and columns. We will number the processors based on which row and column they are. So, the processor holding the top left corner of the matrix is 0, 0. And in this case, the processor holding the top right block of the matrix is 0, 3. From a global, high-level perspective, each processor will compute a local multiplication of its matrix by a piece of the vector and get a local partial result. Then, each row of processors reduces independently their local results to compute the correct value for a block of x1. The result will then be communicated to the correct processors for the following iteration. A particular processor will execute the calculation for a particular block, and it will do theta of n squared over p computation, just like the 1D decomposition of the matrix. But a 2D decomposition will perform less communications. A particular processor only needs a fraction of x0, and will generate a result of a partial value of x1. And therefore, it should only need to communicate theta of n over square root p elements. This is better than the 1D decomposition by a factor of square root p. Let's see how the multiplication happens from the perspective of a single process, since that is how MPI applications are programmed. Let's take the perspective of process 1-3. The process has block 1-3 of the matrix. It also has block 3 of the input vector. The process will compute the multiplication of its local matrix and its local vector, and store the result locally. The local x1 stored by process 1-3 at this time is only a partial value for block 1 of x1. it does not account for the contributions of other processes in that row. So, the processes on row 1 will reduce their partial results onto the process that stores the diagonal block. So, row 1 will reduce its partial results onto process 1 of the row. At this point, the correct values for blocks of x1 are only known to the processes which sits on the diagonal of the decomposition. But, in an iterated MATVEC context, each process will need to know a correct block of x1. The block a process needs depends on the column in which it sits. Column 0 will need block 0, which sits on process 0, 0. Column 3 will need block 3, which sits on process 3, 3. So, process 1, 3 will participate in a broadcast within column 3 and receive the data from the diagonal process in that column. This MATVEC algorithm requires to perform collective communications within the rows and columns of a block decomposition. Collectives in MPI have to involve all the processes of a communicator. So, we will need to create more communicators than simply the word communicator, so we can have row and column communicators. MPI CompSplit is the function that will enable the creation of these communicators. MPI CompSplit will create new communicators so that each process will be part of exactly one of the newly created communicators. The communicator that gets partitioned is identified by the first parameter, and the newly created communicator for a process will be returned at the address given by the fourth parameter. The communicators are created so that all processes that give the same value of color are in the same newly created communicator. Within each communicator, processes are ranked in the order specified by key. Let's look at a code example and run it. After obtaining the ranks in the word communicator, the processes split in consecutive pairs and print some information about their rank. By using word rank over 2 as a color, process 0 and 1 will have the same color of 0. Process 2 and 3 will have a color of 1, and so on. We can see that the new communicators have a size of 2, and the lower word rank process will have rank 0 on the communicator. Then, to confirm the new communicators have split correctly, we generate random values on the processes and reduce them along the newly created communicators. We can see that the reduced values are the same for each pair of processes, which confirms that the reduction happened along the new communicator. Iterated matrix vector multiplication is a cornerstone of distributed memory computing. We saw that how the matrix is decomposed makes a difference in the expected performance of the application. A 2D decomposition performs better, but it also requires a carefully crafted dance of collective operations that will unfold along the rows and columns of the grid of processors, and this requires creating custom communicators. The programming of complex algorithms in distributed memory requires carefully thinking about the problem, and one has to understand the global strategy of the execution, but also the local view from the perspective of a particular process to program its execution correctly.